Hi, welcome back. We are starting the third module of the paper PDE and integral equations. As we know, the third module is uh, of integral equations. So we'll start with the first lecture of integral equation. In this lecture, we will discuss the classification of integral equations. We can start with the definition of integral equations. An integral equation is an equation in which a function to be determined appears under an integral sign. That means the function to be determined means it is the unknown function. So an integral equation is an equation in which the unknown function appears under an integral sign. Okay. So we can classify these integral equations as linear and non-linear. Linear integral equation and non-linear integral equations. Linear integral equations are equations in which no nonlinear functions of the unknown functions are involved. Okay, that is, we can generally use the variable y for unknown function or dependent variable and x for independent variable. So, a linear equation is an equation no unknown or no nonlinear functions of this y unknown function are involved. Okay, that is, linear integral equations are linear in y, that is linear in dependent variable y or unknown function y. Okay, the equations which are not linear are called nonlinear integral equations. Okay, now, in our study, we consider only linear integral equations. Okay. Now, first of all, we can classify linear integral equations. Linear integral. So, we can classify this linear integral equation into two. First one is Fredholm equation. Fredholm integral equations. And second one is Volterra equations. Volterra equations. Now, what is Fredholm integral equation? A Fredholm linear integral equation has the form alpha x into y of x is equal to some f of x plus lambda into integral a to b k of x zeta into y of zeta d zeta. So Fredholm integral equation has this form alpha of x into y of x equal to f of x plus lambda into integral a to b k of x zeta y zeta d zeta, where alpha of x, f of x and k of x comma zeta are non-functions. Okay, these are non-functions. And lambda, a and b are constants. Lambda, a and b are constants. Okay, here the function y of x, is to be determined. This is the unknown function, that is the dependent variable. Y is the dependent variable, so we have to find the solution is actually solution of this integral equation is a function y of x satisfying this equation. Okay, so y of x is the unknown function. Here we have y of zeta lies inside the integral. Okay, now this function k of x zeta is called the kernel of integral equation. Kernel of integral equation. K of x zeta is depends on the variables x and zeta, where x is our variable, independent variable, and zeta auxiliary variable. Okay, so this is the linear Fredholm integral equation. Now, what is Volterra integral equation? If in this Fredholm integral equation, if the upper limit of this integral b is not a constant, if it is the our variable x, then the equation is called a Volterra integral equation. That is, Volterra integral equation has the form alpha of x y of x equal to f of x plus lambda into integral a to x. X is our variable. Okay, our current variable is x. So a to x k of x zeta y zeta d zeta. So this is the Volterra integral equation. Okay. So we are talking about linear integral equation. It can be classified into two, which is Fredholm integral equation and Volterra integral equation. And Fredholm integral equation has this form. In that this integral has the constant limit, and in Volterra integral equation, the upper limit will be the current variable x. Okay. Now we can further classify these equations depending on the function alpha. If the function alpha of x is not equal to 0, then these equations involves the unknown function y both inside and outside the integral. Okay. If alpha is equal to 0, if alpha of x is identically equal to 0, then this y of x, that is the unknown function y of x, lies only inside the integral. Okay, that is, if alpha of x is equal to 0, we have these equations are given by f of x plus lambda into integral a to b k of x zeta y zeta d zeta equal to 0. And the second equation is called it can be written as f of x plus lambda into integral a to x k of x zeta y of zeta d zeta equal to 0. Okay, so these equations are called the integral equations of first kind. Integral equations of first kind. Integral equations of first kind. Okay, that is when alpha equal to 0, the given equations are called integral equations of first kind. That is, this equation is the Fredholm integral equation of first kind, and this equation is Volterra integral equation of first kind. Clear? Now, if the second is, if alpha of x is equal to 1, if alpha of x is identically equal to 1, then we have these equations are given by y of x is equal to this. That is, we have the equations y of x equal to f of x plus lambda into integral a to b k of x zeta y zeta d zeta, and the Volterra integral equation becomes y of x equal to f of x plus lambda into integral a to x k of x zeta y zeta d zeta. So in that case, when alpha of x is equal to 1, then these equations are called, integral equations are called integral equation of second kind. Integral equations of second kind. That means this equation is the integral Fredholm integral equation of second kind, and this equation is Fredholm Volterra integral equation of second kind. Okay. Now, if alpha of x is not a constant, not an is a function of x. It's not a constant, and it's a function of x only. Okay, so it's prescribed function of x. Then these equations are called integral equations of third kind. Okay, integral equations of third kind. That is, if alpha of x is not equal to 0 and not equal to a constant, if it is a prescribed function of x, okay, then these integral equations are called integral equations of third kind. However, by suitably redefining the unknown function and the kernel, it is always possible to rewrite an integral equation of third kind into or in the form of an integral equation of second kind. That is, we can convert. It is also always possible to convert an equation of third kind into an equation of second kind. For example, suppose we have an integral equation of third kind, that is f alpha of x into y of x is equal to f of x plus lambda into integral a to b uh, k of x zeta y zeta d zeta. Okay, if alpha of x is a prescribed function of x, then we have this is an equation of third kind. Okay, equation of third kind. Now if alpha of x is greater than 0 throughout the interval ab, is this interval ab, if alpha of x is greater than or greater than 0, then we can convert this the equation of third kind into equation of second kind. We know equation of second kind is has this form, that is y of x is equal to this. Okay, so here we have alpha of x into y of x here. So this equation can be written as square root of alpha x into square root of alpha x into y of x equal to f of x plus lambda into integral a to b k of x zeta y zeta d zeta when alpha x is greater than 0. Okay, so this is equal to, this can be written as square root of alpha x into y of x equal to f of x divided by square root of alpha x plus lambda into integral a to b k of x zeta divided by square root of alpha x into y zeta d zeta. Okay, now if you are multiplying here with square root of alpha of zeta and dividing here square root of alpha of zeta, then it is an equation. It is a Fredholm integral equation of second kind with the unknown function as this square root of lambda x into y of x. Because here we have square root of, this is the form of form of the second kind equation is this y of x is equal to f of x plus lambda into k of x zeta into y of zeta d zeta. So here y of x and here is y of zeta. Okay, so here this is, if we can take this as we can consider this root of alpha x into y of x as the unknown function, and here it has in under integral sign we have square root of alpha zeta into y of zeta. So this equation is, this is a this is an integral equation of third kind with uh, dependent variable or the unknown function square root of alpha x into y of x. Clear? And this kernel is changed to this k of x zeta divided by square root of alpha x into square root of alpha zeta. We know kernel is a function of x and the auxiliary variable zeta. So it's also a function of x and auxiliary variable zeta. Okay, so it is possible to convert an equation or an integral equation of third kind into an integral equation of second kind. Okay, by redefining this unknown function and or this kernel. Okay, now the kernel is said to be symmetric if k of x zeta is equal to k of zeta x. Okay, kernel is said to be symmetric if k of x zeta equal to k of zeta x, that is if k is symmetric in the variables x and zeta. Okay, it is frequently happens that this kernel is symmetric. Okay, in this converter integral equation also the newly obtained kernel is symmetric. Okay, now in the integral equations we consider usually the functions alpha of x, capital F of x and the kernel k of x zeta are continuous functions in the interval AB. Okay, we are consider usually we consider the functions alpha of x. We know these functions are non functions. We usually we consider these the kernel k of x zeta are continuous in open AB, interval AB. and our solution y of x or our unknown function y of x is required to be a continuous function in AB. Okay. Now, so far we considered the unknown function y is a dependent variable uh, which depends on the independent variable x. That is y, which depends only on one independent variable x. That is, the solution will be y of x, where y depends only on one independent variable x. Now, if the unknown function w depends on two independent variables x and y, that is, we are taking the current variables as x and y, and the unknown function as w. The corresponding two-dimensional Fredholm equation has the form corresponding two-dimensional Fredholm equation has the form alpha of x comma y into w of x comma y equal to f of xy plus lambda into double integral over r k of x y zeta eta w of zeta eta d zeta d eta. So here, this is the form of two-dimensional Fredholm equation with current variables as x and y, and here the auxiliary variables are zeta and eta. Okay, so here the unknown function is w, which depends on the current variables x and y. Clear? So this is the two-dimensional Fredholm integral equation. Clear? Next, we can discuss a simple question. Show that the function y of x is equal to 1 minus x is a solution of the equation integral 0 to x e to the power x minus t y of t dt equal to x. So here the question is to show that this function 1 minus x is the solution of this integral equation. So before that, we can just classify this integral equation. We just try to classify this integral equation. Which type of equation is this? Here we have, this is integral from 0 to x. So this is a Volterra integral equation, and the here from this we get y is the unknown variable or unknown function. It occurs only in the integral. So it is a uh, Volterra integral equation of first kind, because here alpha, this can be written as minus x plus integral 0 to x e power x minus t y of t dt equal to 0. Can be written as this. Okay, so here actually alpha, the function alpha is equal to 0. That is why here the right hand side is 0 here. So we know when alpha equals 0, the equation is of first kind. So this given equation is of Volterra integral equation, of first kind. Clear? Now here the question is to show that we have just to prove that when we replace this function y here by 1 minus x, it should be satisfied. Okay, so when we replace this y of t, so see, we are given that y of x equal 1 minus x, so we need to show that this is the solution. So from this we have y of t is equal to 1 minus t. Okay, therefore our aim is to show that integral 0 to x e power x minus t y of t dt is equal to x. This is what is we need to prove. Okay, so our aim is to show that this integral is equal to x. So this is equal to integral 0 to x e power x minus t. What is y of t? Y of t is 1 minus t dt. Okay, so this is equal to integral 0 to x 1 minus t into e power x minus t dt. So integrating this, we have this is a polynomial in t, and this is a e power x minus t. Here we can take e power x outside. So here, because the auxiliary variable is t, we have to integrate this with respect to t. Okay. So the integral is 1 minus t into integral of e power x minus t with respect to t, that is e power x minus t divided by minus 1. We are integrating with respect to t. Okay. Minus derivative of this 1 minus t, that is minus 1 into integral of this function e power x minus t divided by minus 1, that is integral of that is e power x minus t divided by minus 1 into minus 1 is 1. Okay. Now plus a derivative of this is minus 1, which is 0. I am using here the generalized rule of integration by parts. Okay, so the next term will be 0. Okay, we have integral of uv d uv is equal to u into v1 minus u dash into v2 plus u double dash into v3 minus etc. Where u dash, u double dash etc. are the differentiations, and the suffixes v1 is the first the integral of v1 v, and this is v2 is the integral of v1, v3 is the integral of v3, v2 etc. Okay, so this is the generalized rule of integration by parts. So here the t from 0 to x. So the next term will be zeros because we are different. We need to differentiate this. So next term onwards, we'll get the terms as zeros. Okay. So this is equal to applying this limit. You will get here is 1 minus x into e power x minus x minus x is 0 divided by minus 1. Now when we apply 0, we get minus 1 minus 0 into e power x divided by minus 1. Now here my negative into negative is plus e power x minus x, that is e power 0, minus when we apply 0, that is we have e power x. So this is equal to uh, this is 1 minus x by minus 1, that is x minus 1. Here is minus 1 into this, so plus 1 plus e power x. Here is e power 0 is 1 minus e power x. So this is nothing but it is equal to we can cancel this and 1. So this is equal to x. So we have proved that this integral 0 to x e power x minus t y of t dt is equal to x. That means when we replace the value, or we replace the function y as 1 minus x, this equation satisfied. That means y of x equal to 1 minus x is a solution of the given differential equation. I mean, sorry, integral equation. Okay.